Today we're going to talk about calorimetry. Now, calorimetry is the study of heat exchange between a system and the surroundings. Now, a system is whatever we're focused on. So this is what we care about. So the substance we care about. The surroundings is everything else around it. And in order to look at the heat exchange between the system and the surroundings, we use something called a calorimeter. And a calorimeter helps us figure out a variable within an equation that deals with the heat exchange. Sometimes we can be solving for the specific heat of a substance, or other times we can be solving for a temperature, a mass, any of those variables that are within our specific heat equation. So for the purpose of this class, we're going to be talking about closed systems. And closed systems means that theoretically, no heat can be lost to outside of the calorimeter. So that's what we're going to assume. Now, if we assume that, we can say that the Q of the system is equal to the Q of the surroundings. So basically this means Q meaning heat. The heat of the system has to be equal to the Q of the surroundings. Now, if we're saying that we're talking about a heat exchange, either the system or the surroundings has to be losing energy or heat, and then the other one has to gain. So what we're going to talk about is the system losing energy, so it's going to be a negative Q. So all of the heat lost by the system has to be directly gained by its surroundings. So something that we're going to focus on is water and a metal. So for the purposes of this example problem, we're going to say that all of the heat lost by our metal has to be gained by our water. So all the heat lost by the metal is gained by our water. So let's go a little bit more into this. We know that our specific heat equation tells us that Q is equal to the mc delta T. So this means that the mass of the metal times the specific heat of the metal times the change in temperature of the metal, that's all negative because we're losing that, is equal to the mass of the water times the specific heat of the water times the change in temperature of the water. So theoretically, we can solve for any of these variables. And let's remember that delta T is equal to the final temperature minus the initial temperature. Now, to make this make a little bit more sense, we are going to be dealing with coffee cup calorimeters, and it's something that is just used in chemistry classes because styrofoam cups are really good insulators. And so what we're going to talk about is we have a coffee cup that is filled with some mass of water, okay? And we need to know the mass of the water. We need to know the temperature of the water. And we know that we can find our specific heat of water in our reference packet. And so that's our mass, our specific heat we can find, or we can look up. The temperature of the water, we can use a thermometer. And so that's all we have right now because we just have our initial temperature of the water. Then what we're going to do is we're going to put a piece of metal into this. So we're going to put a piece of metal into the water. Things we need to know about the metal. We need to know the mass of the metal. We need to know the temperature of the metal. We need to know the specific heat of the metal. Now, we're going to say that the metal is going to be hotter than the water. So whatever temperature this is, that means that heat is going to be going from the system, which is our metal, out into the water. Now, to make this a closed system, we have to put another coffee cup on top of it to insulate it so that heat is not being lost to the surrounding air. So any of the heat that is coming off of this metal is going directly into this water. So that means that heat is going to keep leaving zinc until the final temperature of the metal is equal to the final temperature of the water. If a calorimeter is a closed system, we can always assume that the final temperature of the metal is equal to the final temperature of the water. So in problems, they're not going to give you the final temperature of both of them. They're only going to give you the final temperature of one and assume that you know that heat keeps exchanging until the temperature has reached equilibrium. Equilibrium meaning that the final temperature for the metal and the water are the same. All right, so let's see how this plays out in a problem. So here it says, a 2.5 gram sample of zinc is heated, then placed in a calorimeter containing 65.0 grams of water. The temperature of the water increases from 20.00 degrees Celsius to 22.50 degrees Celsius. The specific heat of zinc is 0.390 joules per gram degrees Celsius. What was the initial temperature of the zinc metal? Okay, so let's think about this. We have negative Q of the system is equal to Q of the surroundings. So let's figure out what we know and what we're looking for. So our system is our metal. So in this case, it is zinc. So we know that Q is equal to MC delta T. So MC delta T. If you look at our problem, a 2.50 gram sample of zinc, so we know our mass, is heated, then placed in a calorimeter containing 65 grams of water. So we have our water also. Again, we have the same information. The temperature of the water increases from 20 degrees Celsius to 22.50 degrees Celsius. So our T initial was 20.0 degrees Celsius. Our T final is equal to 22.50 degrees Celsius. So if we subtract those two, our change in temperature should be 2.50 degrees Celsius. The specific heat of zinc is 0.390 joules per gram degrees Celsius. What is the initial temperature of the zinc metal? Well, if we think back, the final temperature of both our water and our metal have to be the same. So we know that the final temperature is 22.50. What we're looking for is our initial. The only other missing piece of information is of our water, but we know that the specific heat of water is 4.18 joules per gram degrees Celsius. So let's go ahead and set up this equation. I'm going to try to make this a little bit less blurry. Hopefully that's a little bit better. Okay, so our system is on the left-hand side, and that is our zinc. So we have a negative 2.50 grams times 0.390 joules per gram degrees Celsius times our final temperature minus X, we don't know what our initial temperature is equal to 65 grams times 4.18 joules per gram degrees Celsius times 2.50 degrees Celsius. Okay, so we want our X by itself. So I think the easiest way to do this is divide both sides by -1, right? Because we want to get rid of this negative. So divide by -1 so that we get 2.5 times 0.390 times 22.5 minus x is equal to all of this multiplied together, and now it's just negative. So 65 times 4.18 times 2.5, and we just negate that. So we end up with negative 679.25. All right, now I want to divide both sides by 2.5 and 0.390. So I end up with 22.50 minus x is equal to negative 696.67. Now I still want x by itself. Since these are subtracted from each other, I'm going to subtract 22.50 from both sides, and I'm going to end up with negative x is equal to, now I do negative 696.67 minus 22.5, and that will get me negative 19.17. Now this is a temperature, right? So it's degrees Celsius. Now I don't want negative x, I want x. So I divide both sides by negative, and so then x is equal to just about 720 degrees Celsius. This is how you do calorimetry problems. Yes, it's a big equation, but if you take it step by step, you can solve for the missing variable.